Okay, welcome back. So I guess we're going to do the panel on robustness, adversarial, and bias and fairness. And then Kyle is going to moderate, and I'll be the co-moderator. So feel free to
thanks a lot for coming back from the coffee break. So these sessions, we're going to cover the topics robustness, adversary, bias, fairness, and deployment in the industry. So we have so first, let me, it's my pleasure to introduce our speakers here. So we have Bo-Chin Gong from Google Research, and we have Wanhan Pantransya from the startups companies focusing on annotating data. We have Olga, who will basically share us about the recent progress in bias and fairness, and also how to mitigating the bias and the privacy concerns in visual data. And then Professor Dina Katapis will tell us about how to basically make the contrast learning robust to shortcuts and generalize to the new modalities. So how about each one of you actually introduce yourself as well. So first, start with from Bo-Chin.
Hi. Hello, everyone. Yeah, this is Bo-Chin Gong from Google Research in Seattle. I work on high-level visual recognition and object detection using limited supervision, especially interested in making visual models generalized to auto distribution, like a domain adaptation, to adversarial examples, including adversarial robustness, and to some corner cases, so including long-tailed recognition. Thanks.
Okay, so Wanhan, do you want to introduce yourself as well? Yeah.
Yeah. Hey, folks. I'm Vahan. I'm one of the co-founders of SuperAnnotate. Actually, the startup and CVPR has a very tight connection to each other because it was created because of CVPR, you can say. I was a PhD student at KTH in Sweden, and part of my research was dealing with pixel-accurate segmentation or unsupervised superpixel segmentation, and CVPR was the dramatic moment in our startup life that we decided with my brother to drop out from a PhD and start a startup. And the reason for that was there were so many annotation companies that they show me that there is a need in what we're building. And yeah, so at the moment we're about 60 people and growing pretty rapidly, raised about $18 million.
So like Olga, do you want to introduce yourself?
Yeah, absolutely. So thanks for organizing this. Thanks for having us. So I'm Olga Rosakovsky. So I'm an assistant professor at Princeton. I work primarily on solving visual recognition, although take kind of a broader view to this. So not just working on particular building particular models for particular tests, but also sort of asking questions about data, asking questions about fairness of these systems, asking questions about the interaction between these systems and people who are going to be using them. So sort of taking a broader look at visual recognition. But I'm, even though I do a lot of work on fairness, I'm very much like a computer vision researcher at heart. I sort of ask all of fairness questions from the perspective of like, what can I, as a computer vision engineer, like contribute to this problem? Some of you may have watched the talk. There's my talk, which is totally fine, but I gave the talk together with my PhD students, Angelina Wang, who talked about a new tool for doing bias mitigation in data sets, with another PhD student, Vikram Ramaswamy, who talked about a CVPR paper that we'll present on Wednesday around essentially using GANs to generate data to try to build less biased models according to some metrics. And then Kayu Yang, who is a PhD student advised by Jia Deng, where we did some recent work around trying to protect privacy of, or at least take some steps towards protecting privacy of people in the ImageNet challenge data, and showed that if you obscure faces in that data set, you can still train models that are accurate and good for transfer learning or accurate on image and challenge classifications on the object classification task, and good for transfer learning, but with the added privacy protection from the face blurring.
And we have Professor Dina Katabis.
Yeah, so hi everyone, I'm Dina Kitabi, I'm professor at MIT, and I'm interested in learning from new data modalities, particularly like if you think about like in computer vision, of course, you are dealing with visible light, but basically much of my career is about how we can use electromagnetic waves. And if you use electromagnetic waves, then you can see through walls, for example, and if you can learn from them, then you can learn to see through walls, but you can also learn from them things that it's not feasible to know using just vision, such as like you can, for example, discover the sleep stage, like not just look at someone saying they're asleep and not, they can discover whether they are in the state when they are dreaming, for example, or not. You can discover a lot of information about diseases, vital signs, and all of that stuff just by analyzing the electromagnetic waves that surround us. And you can do it through walls, through obstacles, and without touching people. And that opens up so many opportunities that my research focuses on.
Thanks a lot. Yeah. So so we're going to go to the like a QA session. So so I have a So first I'll ask a question to Boqing. So I understand like right now there's a lot of works about bringing the transformers into computer visions, from addressing image classifications, object detections, video analysis, to activity recognitions. This is just a new state of art being set up like every day. So yeah, if you watch the different leaderboards. So I have a question. It's like it looks like right now it looks like the transformers right now really becomes like a new CRF or recurrent neural networks, if you may say. So I want to ask the question is what is the from your view, what is the limitations of current visual, like a vision transformers, and what is the future directions of applying transformers to the other maybe like a low levels computer vision problems?
Sure. Thank you. That's a great question. Maybe before answering the limitation part, let me echo what you said earlier. The first part regarding why vision transformers getting a little bit popular in computer vision after they achieve huge success in large language models. To me, sometimes I feel computer vision we made a lot of great progress, a lot of revolutionary techniques, and being borrowed by other fields as well. But then the NLP community, they realized that large language models are so powerful, are able to achieve state-of-the-art results on a lot of downstream tasks by a few short fine-tuning. In this sense, computer vision, I feel actually we are lagging behind. We do not have one single visual model which can abstract all our visual knowledge about our visual world. That's something I feel we certainly want to achieve, want to catch up, I would say. And in order to do that, we need to scale up the data, the compute, and the model. But the convolutional neural networks, we have really strong, nice, but sometimes limited inductive biases. The convolution itself, so it's good, but sometimes also limits the search space because it's pretty specialized architecture of the parameter space. So it's not an efficient way of leveraging the high dimensional space to me. Instead, we remove the constraints, remove the convolution structure using transformer, or even in the future, I would imagine like just multi-layer perceptions. It's fully flexible and fully free for the model to explore the large scale and high dimensional space. Might actually give us some momentum to get a visual model which can abstract our understanding about the visual world. So in that sense, I see transformer is getting popular. It's just very naturally, it should be. And limitations, yes. So global attention, first of all, is still to me an inductive bias. Basically, our assumption about what we want to model about the data it's not necessarily the good assumption. It's very simple convex combination of different signals according to the attention. Its expressive capability actually is not very strong to me. So maybe we should remove or improve the global self-attention such that we can leverage the data a little bit more. So recent works, including visual MLP, MLP mixer, or residual MLP, they replaced the attention by MLP layers, but then maybe they did too much. The results are not as good as vision transformers. So there is a sweet spot between all global attentions and the fully free MLP in between. We are not there yet. We still need some research to reach that sweet spot. So that's very, very personal view, by the way. Yeah, that's the limitation I feel about transformers.
Okay, thanks. Yeah. So Zod, do you want to lead to ask the other question as well? Yeah.
Sure. So this one is for Olga. And so this question is about the revised tool. And it looks really great, but it seems to rely on kind of having annotations for attributes, which may not exist for all data sets. Is there any way to leverage such tool without kind of increasing the labeling burden? And I don't know if, like, a lot of the few shot or unlabeled, unsupervised kind of methods maybe can help here.
Yeah, absolutely. So there's it basically will use whatever annotations are available. So it does run some automatic models for right now. I think it's got some automatic object detection, automatic scene classification. We don't have automatic gender or skin color labeling, just because that seemed like a potentially bad idea, because I think that's gonna just create this sort of self-fulfilling prophecy cycle of bias. But I think, you can definitely, if you're comfortable with that level of bias, you can definitely take some of those off the shelf and run that on your model and just provide that as if it was, provided labels to the tool, and it'll use them. But then it's sort of, presumably if you're doing that, you're sort of aware that to take this with a grain of salt. Whereas I think if we did that, we kind of felt a little bit like we would be giving potentially false information. There's sort of too many caveats there. But yeah, we're working on expanding it, and I think questions about like unsupervised discovery or discovery with less data, I think is kind of at one of the biggest requests we're getting. So we're definitely working on expanding it to make it more usable for the community.
Okay, great, thank you.
Yeah, absolutely, thank you.
Okay, so I have a question for Professor Dina Katabi regarding the, so I know like there's a lot of works around like radars data, and also how to leverage the fact that, you can run like videos together. You can basically get the post estimations, and then you can actually see through the wall using only.
Okay.
Okay. So the question, yeah. So the question I have is like sometimes the radar sensors actually running at a different FPS, while the if you are using the other sensors like a RGB camera, they're running like at different speed, and then technically like how would you actually make sure they're really aligned? And then the second question is like radar data is really difficult to annotate. I know there are some like radar sensors that has like images sort of type of sensors, but really for humans it's difficult to understand. So how we understand, let's say you train our models for detecting persons or analyze the persons in the radar data, how would you make sure that the model is actually doing the correct things?
Okay, yeah. So the first question is about the different frame rates of images and radar. So that it's actually easy to handle, because basically you have absolute time, so you can either downsample or upsample, or it depends on how you want to use the two modalities. Do you want to use the two modalities both as input, or sometimes what we do is that we use one modality actually to create labels for the other modality. But you can always, by using the fact that typically what you are monitoring with images are typically processes that are like you are taking video of, for example, of a person or dog or cat. All of these things don't move that fast. So wireless signals and radios can sample things much, much faster. So you have enough resolution to be able to downsample to the level of images. The second question actually is very interesting about labeling radio signals. So this is of course is a very big problem, and I think it's I mean, whenever you have data modality that we as a humans do not understand, I cannot give you like a clip of radio signal and say, look, I mean, there was one person here in the scene. Can you just identify the head and the legs and all of that stuff? That's just not possible. So, so traditionally to do these kind of supervision, it depends on the task. But like, for example, in pose estimation, you can do a multi-camera system, and you put these like 10, 12 cameras around, and you calibrate them and you synchronize them with the radio signal, you can get labels. But this actually leads to the topic of the presentation that I recorded for this particular conference, which is being able to learn from unsupervised or unlabeled radio signals and unlabeled data. Of course, using forms like contrastive learning, and what the issues are, like how just taking contrastive learning, for example, that we know whether you are talking about like schemes like SimClear or MOCO or BIOL or all of these things. And if you just try to run them over wireless data, they just fail miserably, because what they find is they fail not because they don't learn. Actually, you see the training curve or the loss goes down and they learn, but they learn other things that you are not interested in, because there is so much in the RF data that is not related to the human in the scene. So how can you adjust these frameworks of contrastive learning so that they learn in self-supervised manner the thing of interest and avoid focusing on shortcuts? Yeah, and that is basically what we have this recent project that at a high level, the idea is that you want to keep all of the information by combining contrastive learning with reconstructive learning. So you want to avoid loss of information and focusing on information that you don't care about, and that it eliminates the information that you care about. So you add the reconstructive loss so that you ensure that the features actually keep as much as possible information that was in the input, and then the contrastive loss allows you to align these features in the feature space so that it's easy to classify them using a linear classifier.
Okay, thanks.
So I guess I can ask one kind of related to annotation as well for Vahan. So this question is kind of, what's the future of interactive segmentation? Can we use well-learned models to segment everything, or are there new kinds of interactive mechanisms that are more efficient at annotating images? And I guess you can also, if you want, describe about kind of like Dina was talking about other modalities and things like that, if that's relevant.
Yeah, so when it comes to interactive segmentation, I think what I've seen, there is really like two different ways of doing it. One of them is called this box to polygon or polygon RNN type model. When you put either 2 points or a box or 4 points, then you're trying to predict the mask. And then the other way is really to do like an unsupervised or semi-supervised segmentation and get the segments and maybe do some proposals and then say if it's correct or not. So there are advantages and disadvantages, I would say, in both techniques. So if you're dealing with very obscure data when it's dark autonomous driving scene, superpixels will never work, right? Because you can add the deep learning component on it, so it will really get the pixels right. But often when you really want to correct them, And what we have faced with annotators sometimes, that you give them a task and they're so keen to doing a perfect annotation that sometimes you're having a hard time describing them what is good and what is perfect. And then we need a trade-off between those two. So, and then for the interactive, for the box to polygon type of interactive segmentation, I think the negative sides are sometimes it's really hard to correct, and then those parts that once you did the initial polygon prediction, then if you want to edit the polygon, then oftentimes you hurt and then you get the worst polygon than you would rather kind of do it by hand. So as it goes to the future, in my opinion, we need to use more transfer learning type of techniques where we need to do a little bit of perfect annotations ourselves by manually, and then have worked on few-shot learning algorithms where we will find at first on a large set of data sets new images, and then do a proposal and correct those proposals rather than start doing it either super pixel wise or box to polygon wise. So yeah, I would give a credit to few-shot learning and transfer learning techniques that this will become more or less the future.
Okay. And are you, I mean, I don't know if you have anything to say about like the other expanding to other modalities, since I know there, as Dina mentioned, there's a lot of challenges. I don't know if your company is doing that.
Mm-hmm. Other modalities in terms of like text.
Well, no, it could be other visual or radar or other, spectral. There's lots of different beyond just RGB, right?
Yeah. So at the moment we're heavily concentrated on image and video, and one of the reasons is there are quite so many companies that are building annotation tools. What we realize is we want to go vertical in computer vision and then work on some of those harder problems when, for example, you have a class imbalance problem. How do you create no code required computer vision tools to tackle the class imbalance problem, which is more or less common for all computer vision tasks. So on that end, I would say that we prefer to cover the transfer learning. We prefer to cover iterative training. Data curation system is another one where we already built some tools that helps you to query data, find different type of mistakes really easily. So in this sense, we want to cover the computer vision applications end to end rather than kind of go and build different type of tooling for different applications.
Okay, great, makes sense. Kyle, did you want to ask one? Or did someone else have?
Yeah, I had a quick question, maybe a question for Olga. So I think that works on privacy are very interesting. I saw your work on obfuscating faces. My question is kind of like high level on whether or not you see faces as necessarily being enough, because there are many regions of the body, scars and ways that people walk, and I was wondering if you could just comment a little bit about this and kind of suggest how the field could move forward to help address these complexities.
Yeah, absolutely. Not nearly enough, like not even close to being enough, for sure. I think, so one of the challenges in general with doing like fairness work or sort of privacy, making any kind of privacy claims from like the computer vision perspective is that I think what we are doing is always view it as a necessary, but frequently it is never like a sufficient step to mitigate privacy, to solve fairness. And that's, we try to be like really upfront when we write, just say, okay, this is a first step and this is a necessary step. Like, that if the faces are visible, privacy is being violated. But like, yes, absolutely, there's many other things. And this is honestly one of the biggest pushbacks we've gotten from reviewers so far is like, this doesn't protect privacy. So we keep like toning down the language to say like, yes, it doesn't. But quite frankly, we're not really sure what we can do that kind of goes all the way. Because I think there's not going to be a sense of like perfect privacy protection in these data sets. And I think any claims that it is perfect, I think will be inherently flawed. So we're sort of trying to strike this balance between like what we can practically do versus what would be ideal. And it's like it's never going to be ideal. Similarly, like the models that we train that are more fair, they're never like fully fair. They're more fair according to a particular definition and according to a particular metric, and with a lot of caveats. There's usually a lot of footnotes in every paper, kind of caveating all of these claims. So we're trying to move in the right direction. We're trying to kind of show the field what are some of the tools and techniques that we can deploy that sort of start moving us in the right direction. In the meantime, I'll throw out a plug, but it's way too early, but we're working on collecting other data sets in different ways and sort of rethinking how data set collection should be done, where it would come with actual, we would maintain the fact that it has to be at scale and with the kind of labels that the community is finding valuable for research, but with the consent of creators, et cetera, et cetera. And so we're sort of working on that as well, but that takes longer. And in our experience with sort of ImageNet challenge data, I think at some point this data is, it's so prevalent and the models trained on it are so prevalent that it's very hard to sort of say, well, this data has problems, we shouldn't be using it. It's very hard to do because I think the community, it's just so embedded in a lot of the things that the community is doing. And so what we're trying to do with this work is basically propose an alternative that, like for folks who haven't seen the paper, seen the talk, essentially we've retrained models using this new face obfuscated ImageNet challenge data. And so we show that, for example, transfer learning, across the 4 tasks we tried, like transfer learning is essentially entirely unaffected. And image recognition accuracy drops a tiny bit, less than 1%. And like for any kind of transfer learning using this as backbone should be totally fine. And so hopefully this is the kind of thing that can be kind of a plug and play where the community sort of keeps doing what it's doing, but this is just a slightly better version along this dimension. Again, certainly not perfect, but at least kind of better than the way it was. And we are, in the background working on rethinking data collection with a lot of these questions in mind.
Yeah, great. Thank you.
I have a comment actually about the fairness issue. So one of the things, I mean, of course, we keep talking about like the issue, the problem if that we need more fairness, but actually sometimes people forget that models actually can improve fairness. So let me just give you one example that might be surprising. So we all talk, for example, now with COVID about oxygenation and these pulse oximeters that you use. And these pulse oximeters have a bias against people who have darker skin because they try to measure light through skin. And so one of the things that we were, in one of the projects, we were training to on the data. We use the oxygenation from these pulse oximeters as the ground truth. And now, of course, you have people with white skin and people with darker skin. And the ground truth is known to have that bias. But actually, when you train a model, and because the model does not actually know the skin color, you will see that the model that we train tend to bring these distribution closer. Because the model did not know that this is actually, it tried to create a consistent behavior. We were training the model to detect oxygenation from breathing, but the ground truth oxygenation were biased. So now you see a completely different effect that actually, because the model tries to be consistent based on the observations, and although the labels themselves were biased, now the model is reducing the bias because it's creating a consistent view of the data, of all of the inputs that it was given. So it's not always machine learning and models can create bias toward unfairness. Sometimes actually they reduce the unfairness.
Yeah, I completely agree with that. Thanks for saying. Sorry, I'll just jump in super quickly here. I'll also say I think the most frequent question that I get asked is like, should we be, using machine learning systems at all in any kind of decision making, given that they're biased? And my answer is always, well, at least we can design practical interventions to make them less biased. And again, and at least when we reveal that the model is being racist, the model doesn't argue with us about whether it's racist or not. Like, at least, I mean, people are biased. People are making these decisions in biased ways. And like, at least here we have some hope of designing interventions. And once we sort of know what needs to change, it is more straightforward to change it than trying to change the system of biased people decision making that's in place today.
So actually on that end, I would say that categorical bias, like skin tone bias, for example, is one type of bias, but I would also like to put a lot of attention on who is performing the job, and then there can be like cross-correlation biases. And this is becoming a really interesting problem that I really want to find kind of one professor that will kind of create a problem like this. And since what we're doing is each box or anything that you put, we're putting the timestamp of the annotator role, the time, and who did that, when did that, what class and attributes they put. So when you bring all these different biased terms and then you combine them together, then this is becoming a really interesting problem that you can actually solve, because not always it's, let's say, a gender bias or class bias, but then there is like, who did that? And then maybe it's the person was biased at the beginning, but then they become unbiased, or it's the opposite. So there can be so many interesting problems that there is not really any data set that somebody can kind of create a new field of finding those biases.
Thanks for the discussion. So, so we got the question from to Boqing. So one question is like, will the pre-trained vision transformer be helpful in the other computer vision tasks like object detections? And then the other question is is for Boqing as well as for Dinar. So are the transformer useful in learning multimodal graph data, in learning joint embeddings?
Okay, yeah, I can answer the first one first. Pre-trained vision transformer would be useful for other computer vision tasks, including object detection. You can check the swing transformer paper. They showed that the improved backbone indeed can improve some other fine-grained tasks, in not only object detection, but also segmentation, I believe, if my memory was correct. So that's true. So it's helpful. It's a yes/no question, I guess. The second question is vision transformer. Would it be useful for learning like a multimodal graph embeddings jointly? And the answer is still yes. I want to share this paper. We also put on archive. It's along this direction. We tried to learn multimodal representation from raw video, audio, and text. So the idea is since we have new domains, including the visual data itself, we need a little bit improve not only the model architecture, but also improve the training algorithms. What we showed in the talk was when we kind of enter a new domain with new modality or new models, we need to improve the learning algorithm. Like a CNN in the high dimensional space, they converge at pretty flat local optimum. But vision transformer, if you do not do it carefully enough, it converges at an extremely sharp local optimum. And in the machine learning theory, they have some generalization bounds to show that the generalization capability of the models actually indeed related to the flatness of the local optimum. So by a new optimizer in our paper, we tried to make sure that when the vision transformer converged, it's also actually at a flat region. Surprisingly, that simple change can improve the results by like between 5 to 11%. So that's a lot. So following that, so when you try to, for example, explore the multi-model graph data with vision transformer, highly recommended that look into the training algorithms as well. Thank you.
I have actually a question that came up. So I know there's a little bit of disparate topics here. I'm going to try to tie them together into a hard question. So, you know, I guess it was discussed that kind of models matter, right, in terms of whether they kind of improve or worsen bias. I don't know if anyone knows, like, do large scale transformers that are trained on lots and lots and lots of data, do they produce more or less biased data or biased models? Like, can you ameliorate bias by kind of making sure you get all the long tail kind of, you know, data, like attributes and things like that within the data that you train the models on? Is that an answered question, or are there people looking at this?
I don't think it's an answered question at all. I will post in chat. So we have an archive paper that just came out like on Friday, you know, in time for CVPR. So we looked at like racial bias in captioning, and we specifically look at like transformer versus non-transformer based models. It seems like as there's some very weak signal that as the captioning models are getting better, they're perpetuating more bias. The reason being that sort of the earlier models just aren't really learning all that much detail about the images, so they're not really capturing all of they're sort of saying very generic things, and as the models are getting better, they're becoming slightly more biased. Again, pretty weak signal. We're hoping for a stronger signal, but you know, it is what it is. But there's also, although some evidence that the models that are pre-trained on more data are exhibiting somewhat less bias. That being said, I've actually also been hearing this question a lot over the past couple of days, as sort of like, will, you know, self-supervised learning, open world training ameliorate all bias? And yesterday I was saying no, and today I'm going to say I think it's going to make it worse. I have an even stronger response, because I think the concern is if people are thinking this way, then I think the bias will get worse just by virtue of people are going to be less focused on that issue. Whereas in practice, there's, you know, all of the questions about what is actually the data it's being trained on, and all of the bias questions are, I mean, it's still out in the world, so it'll be in the data.
Yeah, I guess even unlabeled data, obviously, yeah, depending on where you pull it from, is not going to reflect like the full distribution of the world in a way that, like,
actually, I want to add one thing that's the other side of the word in comparison to what Olga was saying. So actually, I believe that contrastive learning reduces bias, but it's because I look at things from a different perspective. The bias that I work a lot with patients and medical data and all of that stuff. So to me, like, some of the bias that is concerning is actually even the bias that doctors have. Like, basically, so whenever you are taking data that is labeled, it is by definition has the bias of the labelers, whether that data is a medical record that a doctor just produced that medical record, or is an image that's coming from a crowdsourced labeling. But basically, when we use contrastive learning, when we are able to learn from the data itself more, it's and particularly if that data is physiological signals, then that can reduce the bias, because that is just standard data that is collected from people directly or from the environment. So it depends on where you stand to some extent.
Can I add a data point to support the Professor Dina Katabe's point? I fully agree. Because I work on long-tail visual recognition, so in the tail, a majority of the classes or the attributes we are interested in are underrepresented. So in the pre-training state, if we use contrastive learning to have instance representations, indeed, existing work show a significant improvement on the underrepresented classes. Just one data point.
Very cool. Thank you. We'll investigate. We'll look more. That's great.
It sounds, yeah, definitely not a solved question. Yeah, cool. I think, yeah, we're running out of time. I know bias and fairness tends to yield the best panel discussions because people discuss a lot more. So yeah, I really appreciate all the panelists coming. I think that was a really great discussion. And I guess the next stage of the workshop, we'll be doing the next set of spotlight talks for the oral papers. Cool. Thank you again.
Thanks so much for having us. Thanks for organizing.
Yeah.
Yeah, thanks.
Thank you. Thank all the organizers.
Thank you.
Thank you, everyone.
So let me find the slides and I will share my screen.
Okay.
Okay, you should see my screen. I believe the REMP author said he felt not well today. I don't know if there's any author from this paper. Okay. Yeah, unfortunately, he said he was not feeling well today. So Shot in the Dark, are the authors here?
Yeah, I'm here.
Okay, so go ahead and just say next slide when you want me to.
Yeah, sure. Hi, everyone. I'm Zitian from UMass Amherst. Today, I'm going to present showing the dark future learning with no base class label. Next slide, please. Future learning is a classical problem that aims to learn novel concepts from only one or very few examples. Next slide, please. Well, traditional future learning methods usually will conduct supervised learning on base classes to learn identifiers, and then later at test time, they utilize this identifier to do the future classification. A unique property of future learning is that it is trained on a set of classes, and then later it is testing on another set of classes. The two sets of classes are destroying, so the training time goal is not very consistent with the testing cycle. Next slide, please. Let me give you an example of what the current future model is doing. Suppose you are teaching your daughter about how to recognize a novel animal II, and you only have one image of this II. So you are trying to doing so by collect a lot of image from Husky and Golden Retriever. You hope that by putting a lot of effort on teaching her how to distinguish dog, she could finally recognize the real II when she go to the room. So do you think she can really do that? From my perspective, I think that even for real person or a model, it is still very hard to do that, because the problem of current future learning setting is that there is only so much we can learn from the base category. Next slide, please. So I'm going to ask, is the current protocol the right way to moving forward future learning? Is there other better ways that we can learn the representation? Because the current model seems to focus too much on learning a generalized representation on base category rather than doing the real future learning. Next slide, please. So let me ask you one question. What if we have an infinite amount of unlabeled data from test distribution? What will happen at this situation? Next slide, please. Well, if we have infinite of unlabeled data, we can have a very large model. We can learn very powerful feature representation, and we can focus less on learning better representation. And maybe we will have a new bottleneck of the future learning, which is how to define category without ambiguity and within only very few examples. Next slide, please. Let me give you an example of this new bottleneck. The left figure here is the color minus character, and this is the limited training class set, and the right figure is the query sample. So only from this training set, do you know this purple 0 should be a 0 or a 9? If you are classifying according to shade, it is a 0. But if you are going to classify according to color, it is a 9. So the point here is it is hard to define a category from few examples. Yeah, I think this is a more interesting problem, and it only occurs when we have a very powerful representation, and that's why I suggest that maybe we can utilize more unlabeled data. Next slide, please. So the traditional opinion often think that if we have more label, we can have more powerful representation. But when we have unlimited unlabeled data, this conclusion does not always hold true, because you already have infinite data. You can learn as much as you want to. So why we need base class label at this situation? Next slide, please. Well, here's another perspective of the use of base class label. If we have example of orange 1 and green 1, both in the base class, and you know they belong to character 1, you know we are going to classify example according to the shape rather than the color. Then we can classify this purple 0 is a 0, but not a 9. Next slide, please. So the conclusion here is labels do not bring better representation, but tell us where to put the attention. So I'm going to highlight that while previous future model usually highlight how to utilize label to learn better general representation, I think that maybe when we have more unlabeled data from test distribution, it will be a better setting that we can focus more on interesting real future learning problem. Next slide, please. So in our paper, we following the direction of having unlabeled data from test distribution and discarding the base class label. We propose a very simple contrast learning baseline. It is just we putting all unlabeled example from test distribution and all example from the training distribution into the data set and train a contrast learning model. And surprisingly, it works very well. And even if it do not use any label from base classes, it outperforms previous state-of-the-art train study or non-train study future learning model. Next slide, please. Well, the point of this baseline is it gives us some hint of how well we can do in future learning and how well we can do, especially when we have unlabeled data from the test distribution, and what will happen if the training time goal is more consistent with the testing time goal, and how many unlabeled data are required to learn a strong future learning model. And also it shows that base class label is not that important. And next slide, please. And if you want to know more about the detail, please refer to our paper, and thank you for your watching.
Okay, thank you very much. Are the authors from a simple framework here? They're not. Okay, I will move on then. Okay.
Yes, can you hear me?
Yes, we can hear you. Okay,
Yeah.
go ahead.
Okay, so hi everyone, I'm Ruggero, and I will present our work, Learning Unbiased Representations via Mutual Information Backpropagation. Next slide, please. So it is difficult to collect a neutral data set in which all categories of interest are observed under all possible distributions. In general, we cannot guarantee that train and test will be identically distributed. Nevertheless, we want our machine learning models to handle such situations. Next slide. So in this work, we tackle the problem of handling dataset bias, which can be introduced with the following example. We have a binary classification problem in which we want to distinguish two classes, namely two shapes. Unfortunately, color is also a predictive factor for the class in such case. So if we let our machine learning model to learn color, next slide, we may erroneously mislabel some test samples, and that's something we don't want to have. So next slide. So among all the possible attributes which are predictive for the class, we only want to learn features regarding those which allows us to generalize, and we want to remove information regarding the bias. Next, please. So our data set is given in such a way. So we have raw input data X, and we have annotation for both the task Y and the bias affecting the data C. So we learn a data representation Z using a backbone, and such representation is then used to perform a class, like a standard classification problem. Next slide. We want to impose an independence constraint, a statistical independence constraint between Z and the bias attribute C. Among all the different independence criterion, we chose mutual information for its capability of accounting for nonlinear relationships among random variables. Next, please. So we can formulate our objective as finding the parameters of our network that minimizes the empirical loss for the task, with the constraint of having the mutual information between the data representation Z and the bias attribute C equals to 0. This can be formulated in this way, in which the mutual information becomes a regularizer. Now, the problem is that mutual information is not directly tractable, so we have to find an approximation in order to optimize this objective function. Next slide. So now I will introduce our method. Next. As I said, mutual information is not directly tractable, so we rely on a parametric lower bound that has been recently discovered. This lower bound is parameterized by a neural network, hence it is fully differentiable. In order to refine the estimation for the mutual information, one has to perform an optimization problem. Namely, it has to maximize this loss function with respect to the parameters of the neural network T. Next slide. So our method consists in a feature extractor, which given as input X produces feature Z, next, which are then fed to a logit layer, which is responsible for performing the task, next. Such features are fed to the mutual information neural estimator, as well as the bias attribute C. So now we see that we are able to make the objective function I introduced before tractable. So the mutual information becomes the maximization of the loss function for the neural estimator. Next slide, please. And more importantly, we can estimate the gradient with respect of the mutual information, the estimation of the mutual information with respect to the parameters data of the feature extractor. In such a way, the feature extractor can perform both the task and the minimization of the mutual information. Next slide. So now I will show some experiments. So we tested our method on the biased colored MNIST, in which color is predictive at training time for the class, whereas at test time, we don't have any correlation between color and classes. We have different degrees of bias represented by the standard deviation of the Gaussian from which the color has been sampled. Next. So we tell the network not to learn the color. And we see that in this way, we can outperform the baseline, which is the standard empirical risk minimization, and other methods that have been previously employed on the same problem. So next slide. So summing up, we learn invariant representation with respect to a known attribute, and we leverage a mutual information neural network estimator in order to remove such attribute by backpropagation. Our approach has been proven to be effective on different computer vision tasks and also on fairness application. I invite you to check our longer oral presentation for more details and our poster. And next slide, I thank you for your attention.
Great, thank you very much. And yeah, just to remind everyone, these will have posters as well, so you can ask questions. Okay, the author from this talk.
Yeah, hi, hello. Yeah, hello, my name is Aritro. I'm excited to share with you our work on contrastive initialization to improve model robustness under level noise. Next slide, please. Yeah, so in practice, you may have access to a noisy data sets where some of the samples are incorrectly labeled for some reason. And in this example, as you can see, the dog has been annotated as, sorry, the bird has been annotated as dog. So as a recap, the most common paradigm in machine learning is empirical risk minimization framework, where you mostly optimize the cross entropy loss, and cross entropy loss is actually sensitive to level noise. So as a reference point, if you optimize cross entropy loss on CIFAR datasets under 90% symmetric level noise, it will perform roughly 40% and 70% worse than divide mix, which is one of the state-of-the-art models. So there are like many others, but it will be in a similar ballpark. So let me start with a simple change in this training structure. If you can go to the next slide, please. Yeah. So what I did is that I just added a contrastive model initializer for initializing that CNN classifier. So if we give the same noisy sample to this CNN classifier, what will happen is that it will still incur high loss, although the model is correctly predicting it as a bird, and it will still get the wrong large gradient direction in the backward pass. But in reality, if you actually train this model with the contrastive model initialization, what will happen is that this will be better than divide mix by 10% and 70% under the same noise conditions. So the point is that we should not that we have to use cross entropy loss, but we want to explore reason behind this observation and like lay out possible reason that we think can be even make this even better. Yeah, next slide, please. Yeah, so there are like many ways you can tackle level noise. So I'll just mention two methods from the supervised category. So one is that you can replace the cross entropy loss with some kind of robust loss functions. There is another way is that you can reweight samples where and learn some kind of weighted risk function. So the general recipe is that you have to pass kind of small gradients for this kind of noisy samples, okay? So if we have like 90% noisy levels, we would expect this kind of model to like remove those 90% samples and learn from rest of the 10% of the probably correct clean sample, okay? So this is good and this is what we want. And in the limit, it will actually find the correct classifier. But in reality, the number of sample is actually limited. So essentially this kind of, this supervised category, what they are doing is that they are training a deep classifier with a much smaller data sets. And we believe that can make this kind of classifier difficult to learn visual representation with level noise in a purely supervised manner. So next slide, please. Right, so one way to mitigate this kind of issue with the supervised robust method is to use some kind of semi-supervised method. So there are like many tricks, but the general idea is that if you have like two diverging models, they can guide each other to exploit even the noisy unlevel samples. So the noisy samples can be thought of as unlevel samples, and you can actually use them to improve your representation learning capability. So we believe that these SSL methods, like semi-supervised methods, robust methods such as divide mix, they perform better than the supervised counterparts because of their improved representation learning capability. So so suppose all that SSL method brings is the improved representation learning capability. So there is no need to throw away those early supervised methods, and we can explore many other alternatives also. Okay, so next slide, please. Yeah, so one of the simplest solution, as we have been seeing in this workshop, is that you can just initialize the CNN with some kind of contrastive model initializer such as Simpler, Moco, or Biol. So the idea is that if we can provide a good initial representation, the hope would be that the supervised robust methods can only focus on the task of learning with level noise and not worry about the representation learning part. Okay, next slide, please. Next slide, please. Yeah, so in this slide, I just plotted one bar chart on a 90% level noise. So what is happening is that cross entropy loss, generalized cross entropy loss, which is one kind of robust loss function, meta weighted, which is a weighting network based function, they perform significantly better than this divide mix or like the state of the art methods if you initialize them with some kind of simpler initializer. But on the other hand, if you start training them with a random initializer, they perform really, really worse. Yeah, okay, next slide, please. So to conclude, we show that those supervised robust methods, they do not learn anything useful under high level noise, but they can be significantly better under with a contrastive model initializer. In fact, even what you do is you train a cross entropy loss that can even beat state-of-the-art methods with the right kind of initializer. And we believe this can actually serve as a strong baseline in future research. So this observation suggests that lack of visual representation is possible reason that many supervised robust methods perform poorly on like image classification tasks, but not on like other modalities where like divide mix kind of algorithms will be probably have difficult beating those things. Yeah, so next slide, please. Yeah, so thank you for watching our talk. For details, please check our paper and the GitHub page, and also please visit us in our poster session. Thanks.
Thank you. That was great. There might have been, I don't remember if there was one that I may have missed. There's some of these came in last minute. Are there any other oral authors from the session that want to present? No? Okay. If that's the case, we can actually have some questions if anyone has any questions. I do have one question for if the author of the MINE approach is here still. Okay, maybe not.
Yes, yeah, I'm here.
So I guess one question is, you know, in that case, I guess you have to, you know, for that data set where you have in the training color is an attribute, but that's highly discriminative, but not in testing. I mean, I guess you have to give it some information about that, right? And so I guess the question is like for more complex things where we may not know what will be, you know, what are like shallow features that like textural or other things that we may want it to weight less versus other features that we think like shape that are important. I guess, is there a way to like maybe expand that to more complex types of imagery and features that we may know what's important and what's not?
So your question is basically how to encode the more complex information, not just color, but also, I don't know, information regarding more complex data.
Right. I mean, I think typically, for example, you know, there's a whole shape versus texture bias kind of work, which shows that, you know, if you can increase kind of shape bias, you can get some improvements in performance. So we know shape is more important than texture, at least for, you know, different data sets such as DomainNet, for example, where you have, you know, natural imagery and then sketches. For obviously, in the sketch example, texture is not important and shape is. Yeah, so is there any way to encode?
Yes, I mean, the premise is that in general, the way you encode information directly affects the final performance of the method, not just regarding our method, but all these methods which tries to make the representation invariant to a certain attribute. So this is a crucial topic and also something which requires further investigation. Regarding this texture bias, I think the most common approach is to encode such information as the gram matrix of some intermediate features, and then you can do some sort of I don't know. Typically, I think it's very high dimensional. These gram matrices are high dimensional, so you have to figure out a way to make it a bit more compact in order to feed it to the mutual information estimator. But in principle, it should work.
I see. Okay. Yeah, I mean, so the typical approach is more kind of training, doing stylization of the data as a data augmentation, and then training on that, and that tends to increase shape bias. But it would be interesting to see if you can use mine kind of approach to do the same thing or better. Yeah. Okay. If there are no further questions for any of these orals, and I did not miss any. Okay, so there's one question at Aritra. What happens when we train the model with noisy labels using supervised contrastive loss? Did you have any such comparison?
What happens when you train the model with noise level using? Okay, I did not do that experiments, but yeah, I think that would be interesting to do. But I think my initial guess would be that if you do with the supervised contrastive loss where you use a noisy level, I think that would make I think it will make it slightly not so robust to the problem. Yeah, I think it will. Like if you have a dog and you are trying to match it with a bird, it will probably the representation learning capability will be hampered. I would say so, but yeah, I think I need to do that experiment and see what will happen. Yeah, that's a good question. Yeah, I should check that. Thanks.
Okay, sounds great. Okay, are there any other questions? Last minute questions? If there are not, then we can, I guess, in like a minute or two, start the next panel, which will be on imperfect, noisy, and weakly supervised learning. And I don't know, Kyle, do you know if all the panelists are here yet?
They're joining right now.
Okay, so we'll wait a few minutes while the panelists join. Thank you.
Oh, Anurag. Okay.
Hey, Anurag.
Okay. Hey, Sadeep. Okay. Let's wait a little bit. So waiting Alex and then I'm free. Okay. Okay. Oh, Alex has not joined yet. Let's just wait a little bit. Yeah. So yeah, so these sessions will we will cover imperfect data, mostly focusing on like the imperfect data, noisy data, weakly supervised. Okay. And then, let's see.
Are we only missing Alex?
I'm missing Alex and also Humphrey. Okay.
Actually, I think they did say they might be, I believe, 10 minutes late.
Oh, okay.
I think I got an email from them, yeah, because they're part of the another workshop on agricultural.
Okay.
So I don't know if you want to start with Anurag, ask questions, or we can wait a few minutes.
So yeah, so I think we have Anurag here. Actually, Sadeep is also here, I believe.
Yes.
Okay. So. Oh, I think Ali Hassani, he said he will be answering question on behalf of Humphrey. So it's Ali's here, right?
Yes, I'm here.
Okay, great. Maybe you can show your videos as well. Yeah.
And Alex just said he's on his way. Yeah.
Oh, okay. Okay. So. Yeah, so let's wait maybe one more minute. Okay. Okay. So if anyone have a question, so feel free to, right now you can post it on the channels and then we can take it there. We also have some question already got it from the YouTube channel as well. So first, I think let's, yeah, is Alex here right now? No? Shall we, so the thought, should we just start it?
Yeah, I think you can start with questions for Anurag and then.
Okay, yeah. So yeah, so first I want to basically introduce each one of you. So maybe first Anurag is going to so Anurag already posted the videos on our YouTube channel. So he's going to cover the video understanding with imperfect data. And then so Anurag, can you introduce yourself as well?
So I'm a research scientist at Google. I'm mostly working on video understanding with transformers at the moment. Before that, I did a PhD at Oxford with Phil Tor.
Okay. Okay, Sadeep, do you want to help to introduce maybe Ali Hassani, who is on behalf of, who is going to represent Hamri Shi?
Hi, yeah, we have Ali Hassani. Unfortunately, I don't have Ali's bio. So maybe Ali, do you want to quickly introduce yourself?
Hi, I'm Ali, and I'm a first-year PhD student at the University of Oregon, and I work under Professor Shi, and that's it.
Thank you.
Okay, it's Alex here. Okay. Okay. I'll ask. So basically, I'll start a question asking like Anurag. So like Anurag, you recently works on like leveraging the transformers for video understanding. So yeah, I want to ask the question. So what actually what is actually unique things you did to make the transformers works for videos? And then what is actually the strength of the method? And on top of that, what is the limitations and what is the future works? Meaning like for like any of those online, what should they work on if they are interested in applying transformers to solving the problem like activity recognitions from the video?
Sure. So I guess maybe to start off, I'd say we were inspired a lot by the sort of vision transformers paper, which is from some other colleagues at Google as well. And sort of one reason we were really interested by it is because they were kind of showing that transformers scale a lot better with more with large data sets and more compute. So by that I mean, if you look at sort of computer vision in the past, it was often, based on these hand-coded features and SVMs and learned features and things like this. And when you had larger data sets like ImageNet, that's when you could train like CNNs like AdXNet and VGG and sort of really learn really good features with them because they scaled a lot better with data than sort of the previous hand-crafted methods did. And you can see with transformers, it's something similar because when you sort of scale your data sets to be larger than ImageNet, so like they use ImageNet 21K in the paper or JFT, you can really see that transformers are able to sort of, I mean that's sort of when they shine and can sort of start really reaching these res nets. So based on that, we sort of, in paper I presented on Vivid, we sort of looked at how you could sort of adapt these sort of models to video as well. So the initial results we have are very promising because it sort of got state-of-the-art results on basically all the data sets that we tried on. But obviously that doesn't sort of mean that we're all done. So one sort of major thing about transformers is that they only work at sort of large scale. So they work when you have a lot of data, but also a lot of compute as well. So these are sort of obvious areas of sort of future work to sort of try. So what you, also want to be able to do is train it with less label data. So like self-supervised works. That's something we're also working on. Also making them more efficient as well, just in terms of like the flops and the runtime and things like this. Also, like when you sort of, because we're talking about video, like sort of like the multimodal aspect is also very very important. But if you want to process more modalities, it means that you be more efficient about it at the same time. And same goes for long videos. So these are all sort of very obvious future lines of work, basically.
Okay, thanks. So Sadeep, do you want to take the lead to ask a question to Ali as well? Yeah.
Yeah, so this is for not Alex Swing's talk, is that right?
No, I think Alice, it's from yeah, Humphrey She's lab. Yeah.
All right, yeah, sorry, my mistake. So yeah, so we have a question here. Looks like the convolutional layers are the trick to make the compact transformers faster. What are the effective operators on transformers to make us choose them over CNNs? And in the NLP results, what exactly? Okay, so that yeah, so maybe we can take one by one. So the question is, what are the effective operators on the transformers to make us choose them over CNNs?
Well, first, going back to the initial questions, the convolutional layers actually do not necessarily make the transformers faster. So it really depends on how many convolutional layers you would use, but essentially the original VIT is using a single convolutional layer. It's just non-overlapping. But the reason why we just switched to overlapping and smaller convolutions, and that actually increases performance but decreases speed. So that's why we repeat convolutions. And generally speaking, primary reasons for choosing transformers over CNNs would be performance, flexible architecture. They're better at encoding relative spatial information.
Thank you.
Okay, so question for Anurag. It seems like there was like a spectrum from less flexible convolutions to more transformers and MLP. So what do you think even more flexible methods such as just MLP, I guess it's like a multi-layers perception. And what are the key trade-off across these spectrums?
So maybe it's worth mentioning that there is a follow-up to the Vision Transformers paper called MLP Mixer, in which case they removed like the self-attention, so there's no real transformer there anymore. It's just based on MLPs. And the point they're making is if you'd use MLPs in the right way as well, then they can also outperform transformers, or at least be more efficient or be on the sort of optimal sort of speed accuracy sort of graph. So yeah, so I mean one of the obvious questions that came up with the sort of Vision Transformers paper with if you saw like sort of is attention all you need, or can you remove the attention and just use MLPs? And so the results we're getting so far seem to suggest that yeah, you can use just MLPs as well. And yeah, you just have to sort of so in MLP Mixer, they sort of do MLPs in 2 dimensions. So in the normal sort of along the batch axis, but also along the sort of like the channel or token axis as well, which is quite important. But I think in terms of what the question is asking, I'd say it is possible to sort of make these really good architectures of just MLPs as well, basically. And self-attention is not strictly needed to sort of get these same kind of accuracies and yeah.
Yep. So I actually asked this question. So I guess my question is like, yeah, it's just in deep learning, there's lots of different patterns of connectivity that you can get to work, and it all depends on how much data you have, how much compute you're willing to do, and then hyperparameter tuning amount and things like that. So I guess what are all the different axes that since everything, lots of things seem to work, right? And each one kind of catches up with the other at various points. So I guess what are the different axes of consideration in exploring the space?
Right. I guess one sort of major thing is that scale is really quite important. So for example, like the Vision Transformers paper, in its self-attention, it's literally the same as attention is all you need. So there's nothing really new there. So people have been trying for quite a while to use self-attention in vision for different tasks, and people usually were trying to put them at the end of the network or things like this. So for me, one of the sort of interesting things about the FIT paper was that it didn't really do anything really new. It was the same with attention is all you need from like a few years ago. But you could see that it only really worked when like the data set sizes were very large, so even bigger than normal sort of ImageNet benchmark. And so the reason we thought for that was I mean, it just got less inductive biases. So when CNNs, for example, used to have the translation sort of equivariance, with sort of transformers or MLPs, you don't even have that either. So to sort of learn these sort of things from your model, you just need even more data. So I think, I mean, one of these sort of things that we're seeing is, well, attention seems to work very well, MLP seem to work very well. I think it's also because we're also working at data sets sizes that we weren't looking at before, and that's quite an important axis. I mean, it's a very practical one. I mean, it's like not very like difficult to sort of just scale your data set size if you have it. But I guess before we didn't, and we weren't looking at that.
Right, okay. And I guess, yeah, related to the workshop topic, I mean, I guess low labeled transformers and figuring out how to get them to be more data efficient, I guess, is ongoing work.
Exactly, yeah.
Cool. So we actually got Alex join us. Alex, he already gave the talks on the YouTube channels about not all unlabeled data are equal. So Alex, do you want to introduce yourself as well? Yeah.
Sure, happy to, and sorry to everyone for being late, just coming off another panel. My name is Alex. I'm an assistant professor at the University of Illinois, working on computer vision and machine learning topics with exciting students. And one of the important topics that we are looking into fits right in here in this workshop. How can we get more out of less, essentially?
Okay, great. So I actually got a question for you, Alex. Yeah, so basically, I mean, like obviously there's like you basically mentioned like three different directions that we can address the like unlabeled data. Not all the unlabeled data are equal. And then, my question is sometimes like for the people's working on like self-driving cars, they need to handle something like detecting cars or persons in the LiDAR data. And obviously you can looking for help from like simulations. But then, so question is like, would that be, so how do we actually address the really the like a bias of the data that actually coming from the graphics data, especially if you just pulling from the game engines?
Right. Yeah, that's an important question, excellent question, and I would argue that there's actually multiple biases here that we are running into. Right. One bias that you see is obviously the computer vision bias. The images don't necessarily always look like real images, even though we're making a lot of progress and we're getting closer and closer to gaming scenes looking like real images. And so there is a bias there, and there's, I would argue, a lot of work on transfer learning, trying to address this and get us closer. But maybe even more important, there's, I guess, a subtle bias in when we create this data. Are we creating data that is, addressing the right situations? And how do our algorithms react to it? Those, are they biased in certain ways to identify scenarios or react in certain scenarios differently than we would want them to react, simply because we're introducing subtle biases that we are not even aware of, right? Imagine you're creating say autonomous driving, you're creating a data set where you have, CG people running in front of a car, and you want the car, to react in certain ways. And now, but by accident, sometimes the hair color of people is, either black or blonde or whitish, and you're not careful about these subtle biases in your data. And your classifier or your models that you're training pick up on these biases without us actually noticing and knowing. And I think these are very important questions, research questions going forward, that I don't think we have an answer to at this point. And as a community, we need to look into those and we need to understand them. As I also alluded to in my talk, I don't think we have answers to these questions, and these are really, really important questions going forward that we all as a community should be looking at.
Okay, thanks. Yeah. Actually, Sadip, do you want to go ahead and ask like a harder question maybe to also Anurag and also Ali? Yeah, I think, yeah.
Yeah, so maybe a question to Anurag. So your work on vision transformers and video, so that's really interesting. Now, so we can see a lot of models like giant models, that sort of things coming out of the researchers working in the industry. So can you comment on like the computational cost of this sort of research and how hard or easy it is for a graduate student working for a, like at a university, for example, to engage in this kind of research, like in terms of resources?
Right. That's definitely sort of a trend that I'd say it's growing even more at the moment, is that some of the models that we are working on really do need like a lot of resources, basically. So the video vision transformers it's even more of a case, because you're working with video, so you need to fit them all in memory. So you just need more GPUs than you would just for an image experiment. It wasn't exactly like this when I was doing my PhD, in that the sort of the requirements we had were sort of a bit less to keep up with the industry. But yeah, that is the sort of the state at the moment, I'd say. Yeah.
I see. So do these models fit into a single GPU, or do you need multiple GPUs to train these models?
Yeah, so everything does fit into like a single GPU. We just for bigger batch sizes to train faster. You just increase the GPUs basically.
Got it. Thank you.
Yeah, so I have actually a question to all of you actually. Like just a follow-up Sadip's question. So let's say, some of the models can only be trained on like a really large, like a GPU clusters, or even pod, which has multiple TPU as well. I know that actually everybody's can have access to those like a beast machine. So question for you is like, so for the those algorithms or models, being trained on like a relatively small data set, and then the model capacity is not really huge. And then they, let's say they show some kind of a progress, getting better result relative to the baseline. Does that actually means, those kind of models can, when they actually have access to bigger machines, like would the kind of conclusions being changed? And then the vice versa, like let's say right now you train like a transformers on like a really super big data set, and with like a really like the cutting edge resources like a TPU pod, GPU clusters, and then when you actually scale it back on like a single GPU, or maybe even on like a CPU levels, does that necessarily translate to be better performance or not?
Okay, so maybe I can start. First of all, that's a very good and relevant question. Starting from your second point, I think it does sort of work backwards as well. So if you sort of validate your idea using, you know, a lot of GPUs and so on, then yeah, I mean, I'd say it usually does work the other way. It's especially, at least for all the transformer work I've done, they all sort of fit on single GPUs and things like that. So it is possible to sort of, you know, train them with less resources. It will just be very slow, and that makes experimenting hard. But all the sort of conclusions that we have would still work, because it is still possible to do the same thing on, for example, one GPU. But the sort of other thing that you mentioned is also quite a valid point as well, in that, I mean, I think this is sort of true for the sort of the community as a whole, but some things like these sort of transform models, they only are really better at large scale. So if you just sort of evaluate, or like if you just tried them on smaller data sets like we were in the past, then you wouldn't really see much benefit from them. I mean, that's the case in vision. It's a case in NLP as well, where the models are, you know, many times larger than they are in vision too. So so basically, if you didn't work at that scale, you wouldn't see the benefits of transformers, and then you would, you know, be sticking to your more traditional methods.
I think we need, I would argue that the real problems that we need to address are actually those problems where we don't have a lot of data. For instance, you know, applications in the agricultural domain, applications in the medical domain. There's a lot of problems and questions out there that I think are extremely important for us as a community to address. And oftentimes in those applications, we don't have the luxury of just even downloading a data set. And the data sets that we then have at our hands are many orders of magnitude smaller than, you know, large scale NLP or even computer vision data sets. And how do we work in those settings? And often there, in these, I guess, models that are developed for really large scale data, like you know, the computer vision community has been looking into, don't easily translate. At least that is our finding. They might overfit, right? And then you don't end up, or your models don't generalize to the problems that you actually really want to solve. And so I guess the one thing I would want to get people to think about is, do we always, let me put it this way, is the only solution to go out and collect larger and larger data sets? Or is that just the current state of affairs because we don't have a good way of learning from smaller labeled data or less labeled data? And so I think, which is why I think, you know, getting people around this idea of trying to work with less labeled data, or trying to learn from corrupted labeled data is such an important area.
Yeah, I'd like to jump in on this as well, because we actually touched on these issues in our work. And we actually did train the original VIT base on something as small as CVPR10. And we saw about 99.9% training set accuracy. It drastically overfitted, but very low test set performance. And what we did is we created smaller and more compact transformer variants that didn't have that problem. And what we observed was that, yes, you could create transformer variants that can be trained on a CPU. We actually tried training a vision transformer, a compact transformer on CVPR10 on a CPU, and in under 30 minutes, we reached about 80% test set accuracy, over 80%, and on a GPU in under 30 minutes, we would get to around 90, depending on the model. And the reason was that the models were just basically very small, and we saw that they could compete head-to-head with many convolutional networks of equal or similar sizes. And we saw that many, we actually compared to convolutional models that beat us, not by a lot, but those that only train on the CVPR10 training set and not extra data. And those were actually a lot more complex. They took a lot more resources to train than our models. And I would say that we actually explored this because one of the reasons was that, yes, in fields like agriculture, as you mentioned, or even medical imagery, there's always, we usually don't have a lot of data available. So it would, and pre-training on not even image, not even something as large as JFT would probably not give us that much of give us an upper hand as opposed to training using convolutional models.
Yes. Okay. So we actually got a new questions coming. Yeah. Thanks for the answer. So one question is from Lars. Actually, he asked in the real world scenarios. Sometimes we have to dealing with like so obviously you will got like annotators, and then sometimes the annotators they disagree with each others, and then in the extreme cases like 50% of them choose. For example, choose class A, and then the other choose class B. How do you handle, or how would you actually handle them? Yeah, I guess there's actually tendencies in the computer vision community is that say when the convolutional neural networks arrive, and then everybody switch to convolutional neural networks. When RNN arrive, everybody switch to RNN, and then when now it's time for transformer. So is the transformer to these answers, or do we? What are the directions can we actually use to address these issues? Yeah.
Yeah, I guess one direction that one could think of is label smoothing, right? People have found that in label smoothing as a data augmentation tool can often actually help. So when you have this, I guess, as Lars mentions, when you have these fuzzy labels, is that a good thing or a bad thing? It's not always the case that you can agree on certain decisions. Again, giving an example from the medical domain, for instance, while in the majority of the cases a diagnosis is pretty clear, often, particularly if you're in a gray area, right? You go to two doctors and they might give you a different diagnosis, and what do we want? What do we want the model to do in those cases? Do we want the model to agree with one, or do we actually want the model to kind of represent this form of uncertainty? And I would argue representing this form of uncertainty is not necessarily a bad thing. So I'm not sure, even if you have fuzzy labels, that you would actually want to resolve those. But the labels might be fuzzy for a reason, that we do not agree on the result either. And maybe one should treat that as I guess a benefit rather than a disadvantage if one has those, if your particular application that you're thinking of has these fuzzy labels. But I'm curious to get to know what other people think about that too.
Yeah, I mean, just to add to that, I kind of agree with it too. I mean, in most standard data sets, we always have, one hard label, but I mean, you don't have to have this. And I mean, I think soft labels can be, a feature and not necessarily a bug. So if you have them, then I mean, I don't see any reason why you shouldn't want your model to be predicting soft labels. And since we've been talking about real world data and things, maybe something that's underlooked in our community is looking at the calibration of models and also looking at the uncertainty of them. And like if we actually have these kind of labels, it actually might help to like look at these problems actually.
Okay.
Yeah, actually, I mean, based on my experience, we actually seeing these problems in the past. So usually, what we do is we delete the data actually, or maybe we don't use the data at all if the two guys disagree each other's. And then what we do is we train our models on a more consistently labeled data set, and then we use the models to predict on this data set. So to actually acquire the labels. Or maybe just just discard this instance at all. Yeah.
Right. One point I could add there is, and I talked about this in the presentation as well. You can try to learn a weight for how much you actually trust your data. I guess we talked about this in the context of not all unlabeled data are equal, but I could easily argue not all unlabeled and labeled data are equal, right? Some data you trust more and other data you trust less. And what you could do is try to formulate this such that you can actually give a weight to data points. And then you let your training progress decide how much to trust which of the data points. Obviously, that only works so far, because if I can switch my labels around in an arbitrary way, my model wouldn't do anything meaningful anymore, or I have no guarantees what my model does. But I would think there's a lot of opportunities here too to try to understand how much to trust individual data points as opposed to just throwing them away.
Yeah, that makes sense. The other question, let's see. Yeah, so Anurag, so I mean, I think you have actually the other works which using multi-instance to address. I mean, like you basically model the uncertainties in for the weekly supervised learnings. I mean, according to your experience, like, I mean, the kind of general questions I have is like, so surely you can actually train the models doing the like weekly supervised learning, but then so the kind of typical evaluations shows that usually those kind of methods is actually inferior to the the fully supervised trained models, right? So and then so the other thing is like if you sort of increasing the number for like a training set you use for, because you're using weekly supervised learning, presumably you can get access to more data. Like in your experience, like did you see the real benefits in the real world applications that those weekly supervised learnings can actually help improve the state of art?
Right. So actually, with respect to the second part of the talk that I talked about with the weekly supervised and predicting uncertainty to help you deal with the noisy data even when you have it. One sort of benefit that we actually observed in sort of a practical use case is that it literally actually did help a lot, because there was simply some task like this was an actual detection in like videos where it was literally very expensive to go out and label this kind of data, and it was you could either sort of label one video per frame with these bounding boxes, or you can label like 100 videos with just these sort of like weak labels. and when you sort of just look in that sense, in like in that scenario, it basically, I mean, it basically helped a lot to be able to do this, because otherwise it just wasn't feasible, like in terms of cost, to go and label like a fully supervised data set. Yeah, so I mean, in that kind of case, because we did have a real world sort of application where we couldn't go out and collect a data set, or we didn't want to sort of pay the cost and time. So I mean, in that case, it was very helpful actually. Yeah, so I mean, maybe if you want to sort of compare the weekly and fully supervised methods, it's like you can maybe say, well, if my budget is this in terms of dollars or time, what sort of models can I get? And at least for one sort of use case that we had, it was very clear that the weekly supervised method was much better because of this.
Okay, thanks.
Yeah, I guess we have the poster session, so I guess.
Okay. Yes, thanks everyone for joining us. Yeah.
Cool. Yeah. Thanks for the panel. That was a really interesting discussion. There's a lot unknown about transformers and other architectures. So right now is the poster session time. And so I will show some slides on if you don't know how to join. And then I'll actually stay on the Zoom. I can join live. I don't know, it might break my computer if I do both, but I can try. But first, let me just, again, all these slides are on the webpage, linked from the news section. But again, the key thing is just load up the CVPR workshop element item, and then there's a Gatherly link there. Once you click on that, you have to give them access to your camera and audio. And then you should be able to essentially join into this forum here. And the first thing you'll have to do is double click on this elevator here. And that will give you a list of floors, so to speak. And you'll see 2 for this workshop, L2ID poster session. So there's 2 rooms for half the posters and the other half. Once you click on that, then you're going to be here in the poster room, and essentially you just double click on where you want to go spatially across this poster room. If you're a poster presenter, just go to your number, which is in the list of papers on the webpage. And then when people go next to you, you can share your screen where you can share your poster. So here, once you're here, if there are 2 people here, you can click this share link, share screen button to share your screen if you're a poster presenter. If you're just attending the poster session, you just move around and jump around and meet people, and hopefully they'll share their poster and you can talk to them and ask questions. Let's see. Yeah, so that's the summary. Again, all of this is from this platform guide that you should have gotten if you registered for CVPR.
Sorry, I have a question. Posters have letters assigned, not numbers. I guess we just mapped it.
So if you go to the webpage, we do have numbers assigned.
Oh, okay, sorry, I don't see that.
So if you go to I think you can see my browser.
Yeah.
If you go to the list of papers here, list of accepted papers, there's a number here for each paper.
Oh, got it. Okay.
Of course, I mean, in the end of the, like, find the spot and people will come to you, but just, yeah, make sure to, ideally go next to your number, but, stand somewhere in a poster so that people know that they can jump to you and talk to you.
Yeah, thank you.
Yep. Any other questions? I can try to do this live. Let me turn off my video. I don't know if it'll work because now I'm doing 2 things at once. Let's see. share my screen. Okay, you should see my screen, and this is the Gatherly. So you just select which webcam. Again, I gave it permission earlier, so it'll ask you to get permission. You select the right microphone here. It always chooses the wrong one by default. And then you join. And so here you go to the elevator. And that loads up this L2ID. And there's already people there, so we can jump and select people and you can talk to them. So what, yeah, I'm testing, I'm showing everyone how to use Gatherly. Can you hear me? Oh, he cannot hear me. Okay. Anyway, so that's how you do it. So yeah, just open Gatherly, double click on the elevator, go to the right one. There's two of them, and then just go next to the people. It's a new experience for everyone, I think. So let's see how it goes. Cool. And then we will come back for the next panel session, which will be, let's see. So the next panel session will be at 2 p.m. Pacific or 5 p.m. Eastern. So, cool. Thank you.